Good morning and welcome to Municon. I'm Nigel Pickering with the Washington Stormwater Center and WSU in Pullman, and I'll be moderating this presentation entitled Biomass Production on Vegetated Filter Strips. It's pre-recorded. It's by Hisham, El-Husseini, and others from the University of Washington, Gustafson, Heidi, Gough, and Renata, Bura. And with that, I'll turn it over to Hisham.
Hello everyone, my name is Hisham El-Husseini, and today I'll be presenting our research, which is biomass production on vegetated filter strips. So vegetated filter strips, or VFSs, are slightly sloped vegetated areas, as shown in the pictures here. They can be designed to treat highway runoff pollution, and they do so by filtering out suspended solids, permitting time for a runoff to infiltrate underlying soils, or encouraging biological uptake through the vegetation. Maintenance for VFSs can be costly as they require periodic inspection, cleanup, mowing, and weed removal. It's also important to note that if the vegetation cover of a VFS drops below 80%, it may not be effective. So we come from a bioresource background, so we see VFSs as not only a way to reduce highway runoff pollution, but also an opportunity for us to produce biomass on marginal land. So in a biorefinery, the goal is to convert biomass to renewable fuels and chemicals. However, an issue with biorefineries are that the feedstock costs are very high. And so this is a graph that shows the operating costs of a biorefinery. And you can see that the feedstock costs account for the largest portion of operating costs. So we could produce biomass for the biorefinery feedstock on the vegetated filter strips. And that brings me to the shared cost model between two parties, and that's a transportation agency and a biorefinery. So the transportation agency is likely interested in reducing highway runoff pollution, and a biorefinery is interested in lowering their feedstock costs. So vegetative filter strips offer a solution to both of these goals. So the overarching objective of this research is to reduce highway runoff pollution and produce a low-cost biorefinery feedstock. So I'll be looking at the pollution reduction efficacy of implementing vegetative filter strips on major roadways in Western Washington, and also I'll be looking at the feedstock cost reductions associated with that. So this brings me to the first objective, and that's assess the efficacy of pollution reduction through implementation of roadside vegetative filter strips in Western Washington. So to achieve that objective, I use these two equations. The first one is the current annual storm load. So the annual storm load is the amount of pollutants that are discharged to the environment through the vector of highway runoff pollution in Western Washington. So to find that, we look at the roadway area and assume that any runoff that comes off of this roadway area will have a concentration according to the event mean concentration. And so we can multiply all these together, this volume by this concentration, to get the amount emitted every year. For the annual storm load, after VFS implementation, we use that current annual storm load and we subtract the amount of pollutants which we can remove through the vegetated filter strips. And so to do that, we look at the roadway area that can be treated by the vegetated filter strips, multiply it by the average annual rainfall to get a volume of runoff that can be treated by the vegetated filter strips. And then we also use the event mean concentration and then the VFS removal rate to see how much we can remove. And then we subtract that from the current annual storm load to get the new annual storm load for vegetated filter strips. So I'm now going to go through each of these variables and show you how we got to them. So for event mean concentration, or EMC, this is the concentration of pollutants in highway runoff during a storm event. I got this data from the WashDOT Highway Runoff Characterization Report, and which is this table here. So these are the pollutants of interest. We're looking at suspended solids, phosphorus, nitrogen, copper, zinc, and lead. And the EMCs for urban and rural roadways will be different because those roadways kind of have different uses. So we need different EMCs for each of these pollutants in these cases. Next, I need to determine the roadway area. To do that, I use these three maps. So the county map, a major routes map, and then an urban rural road map. We start off by clipping the county map to just Western Washington. And so now we can establish our geographic region, which is just Western Washington. So I'll clip these other maps. So now we're left with this major routes map. We can zoom in on it. And as you can see, these are all lines, but we do need a surface area in order to get that volume. To get the surface area, each of these lines has underlying data that represents the width of that. So I can buffer each of those lines with that data. And that gives us the roadway area map. So now we have a surface area of the roadways in Western Washington. So now we need to classify them as urban and rural. So this is the roadway area map zoomed in on a different location. And we can use this urban rural roadway area map to classify this. So as you can see here, this yellow roadway area is rural, and then the pink roadway areas are urban. Next, I had to determine the potential VFS sites in Western Washington. To do that, I used these 4 maps. So we have the county map, a tax parcel map, a major routes map, and then a national land cover map. And this national land cover map has data for pixels that represent different land cover types, which could be open water, developed land, forest land, barren land, grassland, etc. So we can use that to determine where we can put the vegetated filter strips. So first thing I'm going to do is clip all of these to Western Washington. Okay, and now we have these 3 maps. And so we can only establish vegetated filter strips within the Washington state right-of-way. But unfortunately, there was no right-of-way map. But I did find this tax parcel map. And under the assumption that only that public land is not taxed, we could invert it to find the right-of-way. So I'm going to zoom in on this tax parcel map and on this roadway area map. And as you can see, this is the roadway area, and it's not taxed. There's no pink parcels over there, which means it's right-of-way land. So I can invert that to get the right-of-way, which is shown here. And now I'll just zoom in on the land cover map on the same spot, and we can clip the land cover map with this right-of-way data. So now we have a right-of-way map that shows the different land types within it, and we can make some assumptions that VFSs can be established on barren land, grassland, shrubland, and open land. So we can select for all those land types, and that leaves us with a VFS map. So all these green parcels are potential sites for implementing vegetated filter strips. Next, we need to determine the roadway areas that are adjacent to VFS sites because these are the roadways that can be treated by the vegetated filter strips. For this, I use the VFS site map, which I just derived, and then the roadway area map, which I derived earlier. If we zoom in on both of these and then overlay them on each other, this is what it looks like. So this gray part is the roadway area, and then these green blocks are the potential VFS sites. So now we can just select roadway area fragments that are adjacent to these VFS sites. And so that's what it looks like. So now we have a VFS roadway area map. And so these blue roadway areas, these represent roadway fragments that are treatable by VFSs. So we're assuming that any runoff emitted from these roadway areas gets treated by the VFSs. Next, I look at the VFS removal rate. So once again, we're looking at all these pollutants of interest. And I used 4 different sources. And then I kind of just took an average for the VFS performance that we're going to be using in this analysis. So just as an example, for total suspended solids, runoff passing through this vegetated filter strip, about 50% of the total suspended solids will be removed from that runoff before it gets out of the vegetated filter strip. So back to these 2 equations, to solve the annual storm load, the current annual storm load, we first looked at the event mean concentration, then we looked at the average annual rainfall, and then the roadway area. So we can multiply these 2 together to get a volume of runoff that's emitted from the roadways every year. And then we can multiply that by this concentration to get an amount of pollutants that are emitted every year. To solve for the annual storm load with the VFS implementation, we use the current storm load and then the VFS roadway area and average annual rainfall. So this volume here is the volume of runoff that can be treated by vegetated filter strips every year. So we can multiply that by the event mean concentration to get the amount that can be treated, the amount in this volume that's treated, and then we apply the VFS removal rates to see how much, or find the amount of pollutants that are removed from this runoff every year. And we subtract that from the annual storm load to get the annual storm load with the VFS implementation. So this brings me to this conclusion, or these results. So this is the total pollutant reduction. So this is the percent reduction of each of these pollutants of interest that could be achieved by implementing vegetated filter strips in all those potential locations. So we could see that total suspended solids, copper and zinc, they can all be reduced by almost 25%. And then we have phosphorus and nitrogen that can be reduced by almost 15%, and then lead that can be reduced by almost 20%. So for the conclusion for objective number 1, we can see significant reduction in pollutants discharged through highway runoff if we were to implement vegetated filter strips in all those potential locations. And then we have large reductions in pollutants of concern, specifically 26% of the suspended solids, or the suspended solids emitted can be reduced by 26%. The copper emitted can be reduced by 24%. The zinc emitted can be reduced by 27%. And then the lead emitted can be reduced by 21%. So moving on to objective number 2, now we want to assess the potential supply and cost of biomass produced on roadside vegetated filter strips in Western Washington. So for some assumptions here, we're assuming that there is a biorefinery operating in Centralia, Washington. We're assuming that the biorefinery's capacity is 150,000 tons of poplar per year. So this biorefinery is processing poplar into fuels and chemicals. And then we're also going to be using a harvest and ship model. So in this harvest and ship model, the biorefinery and the transportation agency will be sharing costs in order to establish and maintain and harvest those vegetated filter strips. To do this, first, I need to find all the potential VFS sites, which we did earlier. Then I need to look at the biomass production economics, the transportation distance from each site to the biorefinery, transportation economics for that, and then finally a supply curve that's made from all this data. So for roadside biomass production, that will be happening on all the VFS sites. And so that was derived in the map earlier, and this is that map in a zoomed out version. So all these pink circles are potential VFS sites. The larger the circle, the larger the site. And then this yellow square is the Centralia biorefinery. So moving on to production economics. So we modeled growing poplar on the vegetated filter strips. It isn't ideal to grow poplar on the roadside. However, we chose poplar as our biomass of choice because we have a lot of economic and growth data for poplar and conversion data as well. And it's important to note that this analysis can be reproduced with any type of biomass. We just chose poplar because we had all that data available. So anyways, for production economics, we have some different phases. We have site preparation and establishment. We have an establishment cycle where we have crop care and harvest, and then a coppice cycle with crop care and harvest, then restoration and administrative expenses. So over here we have dedicated poplar, and then we also have roadside poplar, which is the VFS poplar. So dedicated poplar is poplar that's grown on a tree farm, and the purpose of growing it is for an energy crop for conversion at a biorefinery. Roadside poplar is poplar grown on a vegetated filter strip, and so this has shared costs with the biorefinery and the transportation agency. And so as you can see, it's missing a lot of values here, and that's because we're using that shared cost model. So in this case, the transportation agency will be responsible for establishing the vegetated filter strips, doing a little bit of maintenance on them. Then the biorefinery itself will be doing the mowing, or in other words, harvesting the crops and then transporting them to the biorefinery. So we can add all this data together to get a farm gate cost. And we can see that dedicated poplar costs about $50 per ton at the farm gate. And then roadside poplar costs $27 per ton. So we can get big savings on the farm gate by using that shared cost model. For transportation distance and economics, I use GIS Network Analyst to find the shortest route from each different VFS site to the biorefinery. We used a price of 31 cents per mile per ton to transport the biorefinery. And then we also added a backhaul cost, which was half of the transportation cost. So these are the supply curves that I was able to make from the farm gate and transportation cost data. On this y-axis, we have the average cost in dollars per ton, and then the capacity on the x-axis, and that's in tons per year. And so the red supply curve here is dedicated poplar for reference, and the blue supply curve is the roadside poplar. So as you can see, the roadside poplar is much cheaper than the dedicated poplar at these low capacities for biorefineries. But as we get up to the highest capacity possible for roadside poplar, it becomes more expensive than dedicated poplar. And that's mainly because since the VFS sites are a lot smaller than tree farms, we eventually have to travel further and further away in order to get them. So the transportation costs end up making it a little more expensive down here or up here. So we can combine these supply curves together by taking the next cheapest source of biomass and assimilating it into the supply curve. So I do that here. So now this blue supply curve represents the dedicated poplar and roadside poplar supply curve. So the combined supply curve has a large capacity and is much cheaper than dedicated poplar at all times. So at 150,000 tons per year, dedicated poplar costs about $76, and then this mixed supply curve costs about $66 per ton. To conclude objective number 2, there's about 90,000 tons per year of roadside poplar available if we were to implement all those vegetated filter strips. And then at a biorefinery capacity of 150,000 tons per year, we see 13% cost reductions in the feedstock. And then we can get even higher cost reductions if we were to go for a lower capacity biorefinery. Not only that, but we can combine the roadside poplar with other alternative feedstock sources that are low cost, such as agricultural wastes or other feedstocks that provide ecosystem services, and get even higher cost reductions at higher capacities for the biorefinery. To summarize it all, the biorefinery benefits are we can produce a low carbon fuel that can more easily compete with the current traditional fuels out there today. And then we can get a lower cost biomass to just make it more economical. For transportation agency benefits, we're reducing the amount of runoff pollution, which is a major threat to waters in Western Washington. And then we can lower the cost of the VFS maintenance by offloading the mowing to the biorefinery. Thank you for listening to my presentation. Does anyone have any questions?
Okay, if anyone has any questions, please type them in the chat box, and I'll read them out, and we'll get them answered. So there is one question so far. It says, and it was, I think it was an objective 1. It says, what is the adjacency criteria?
Right. So I think that's referring to the VFS being adjacent to the roadway. So we kept that really simple. The way we selected roadways that were adjacent to VFSs was they're just within 50 feet of it.
So just as a follow-on, is that a setback where you would not grow biomass?
Sorry, what was that?
Would that be a setback from the road edge where you would not grow biomass for some safety reason, or?
Oh, no. So this is when we were trying to find roadways that were adjacent to vegetated filter strips so that we could know if the stormwater coming off the roadways were treatable by those vegetated filter strips.
So that's a connectivity issue.
Yeah.
Okay, we've got some other questions. Are there any safety concerns with Popular being installed in right-of-way? Do you need guardrail
Yeah,
installation?
right. So I don't think poplar is a good choice of biomass to install within like the right of way on the roadsides. But this research is reproducible with any other type of biomass. So like some sort of grass would probably be better.
There's another question. Does Popular or other biofuel plants take up lead or other pollutants from roadways? If so, how would that affect the biorefineries? That is
Right.
the waste produced.
Yeah, I think they can take up metals. I'm not really sure how that would affect the biorefinery. It could cause some problems with the equipment in the refinery. But I guess we can't really know until we try it out.
Can you just maybe explain what the gate farm term is and where it came from?
Yeah, so farm gate cost is like the cost of biomass when it's at the farm. So you have to do a bunch of stuff like establishing the biomass on the farm, harvesting it, using fertilizer or herbicide or whatever you need. So you take all those costs, and so that's before it leaves the farm. You look at the costs there, and then there's also transportation costs. So you can add the transportation costs to the farm gate cost to get the cost of what the biomass would be at the biorefinery. Oh, I think Rick.
Yeah, Rick wanted to say something about the lead question. Is he, we'd have to have our Zoom moderator let him in.
Rick, you are able to unmute now.
Okay. Yeah. So the metals wouldn't cause any problem at the factory. All those would end up in the ash in the boiler of the factory. So there'd be no, and it's not enough of it. The poplar would take up lead, and that they take up all the water, and then it ends up in the biomass. But in the process, it would just end up in the ash of the process. And there's not enough in there to mess it up.
Does anyone else have any other questions? So this biorefinery, is it primarily to produce energy? Is that the?
Yeah, so it can produce a whole range of chemicals or fuels.
Okay. All right, I'm not seeing any other questions. So I think maybe we could end early. So I want to thank the speakers today and enjoy the rest of the conference. Thank you.
Thank you.
Thank you.